All right. Hey, everyone. GM. Welcome to another NoirHack workshop. Today, I'm joined by Michael, a compiler engineer on the Noir team at Aztec. So he will help us walk through a more advanced session where he'll go into unconstrained functions and optimizing performance. So I will hand it over to Michael. Michael, go ahead.
Hi, great to see everybody. As Rafi mentioned, I'm Michael Klein. I'm on the Noir team, and today I'm going to be talking about unconstrained functions, specifically for optimizing performance and doing some things that might be hard on non-CK languages. So unconstrained functions look like this in Noir. They look like a Rust function where you write unconstrained instead of pub or in addition to pub. And I'm going to talk about a broad, mostly strategy-based, with a couple examples, approach to how you can use unconstrained functions. I'm going to talk about NP complexity, how they can be used for searches, special cases for invertible functions, a general pattern about validating and connecting the input and output. I'll talk about composing unconstrained functions and things around performance for that. And then finally, I'll talk about profiling and debugging performance. So first of all, NP complexity. So NP complexity is closely related to the scope of programs that can be easily translated to a zero-knowledge proof. And this has been studied for quite some time. There's an open problem called P versus NP, which basically asks if it's easy to check that a solution to a problem is correct, it is also easy to solve the problem. And this is a $1 million prize that has many pages of published research on studying it and optimizing it. And in short, if your problem is in this scope of already being tightly studied, it's worth checking whether you could just use the existing solution. There's over 100 problems that have been highly digested and identified to be NP complete. Some of the most popular ones are Boolean satisfiability, integer programming, and graph coloring. These can be applied to very broad things such as Boolean satisfiability for permissions, integer programming for pretty much any time you have discrete resource constrained actions. It may be applicable. And graph coloring can be used in a similar way for more social or network constrained actions. So how do you go about doing this? Because again, there's a lot of existing research. Well, how I approach it is I start by saying, does it look like a popular NP problem? I have a small list of NP problems like SAT and integer programming that I'm a bit more familiar with because there's more solvers and translations for them. And these, because they have the most attention, there's often international competitions on maximizing speed for these. So if that doesn't apply, does it look like one of these commonly known problems? Because it might still be possible to wire together some translation to Boolean SAT, for example. A lot of people will just translate to SAT as like a first approach, but there can often be a lot of overhead doing it just directly. And somebody's probably already studied how to reduce that translation cost, which can be polynomial. So it's worth looking at the existing research there. And then finally, can you do a kind of a fresh translation efficiently to an NP problem? And if not, kind of the rest of the talk is for those cases where it's not obvious that somebody's already put a ton of work into it, and we know we want to optimize things with unconstrained functions. But I'm leading with this, even though it's NP complexity is one of the first things that's also often mentioned with zero knowledge, because if I could totally answer the question of when to use unconstrained functions and when not to, I'd have $1 million. So it's just to make it clear that this is pretty challenging. All right, so one of the first things that we can do, as I mentioned before, is accelerating searches. So you've probably already seen this general pattern, but may not have applied it to unconstrained functions, and that is Merkle tree access. So what we can think of that is an unconstrained search for the element of the tree, where we don't have any constraints. We were literally just like doing a database search, so to speak, and then we're looking in that for the final path in the Merkle tree. And then the constrained side is just the check of that Merkle tree path. This can basically be extended to many other types of searches where we need to find a needle in a haystack, which basically can be done in unconstrained or kind of out of band, but then we might need specialized data structures to prove that there's no needle in the haystack. And this is, while a lot of algorithms require some amount of searching, it's often like only one component. So I'll give some examples where this can be used a little bit more broadly. So I mentioned that we might need specialized data structures to tell that there's not an element in the list. And one example that is a little bit involved, but I think it illustrates the point, is that if we take a doubly linked list, so we have each element of the list, we can go forward or backwards in constant time. And we back that with an arena because we don't have arbitrary memory in a circuit, and we sort that list. Well, now we can search to the middle of the list in unconstrained, where we need to add or remove or prove the non-existence of an element. And then in constant time, we don't have to look at the whole list anymore. The constrained side can only look at our target element or our target slot for an element, as well as the immediate smaller and immediate larger elements. And this is kind of a general pattern. If we can convert the validation into a constant time or nearly constant time check, then everything else can be done out of band and unconstrained, and we get, in my mind, basically ideal performance for this part. Now, of course, doing the actual check itself, we might want to optimize that, but at least it's split efficiently. For a slightly more involved example that I can't claim is solved, but it shows how it can be a little bit more nuanced, there would be parsing parentheses. So when you're parsing parentheses, normally you might use like a stack or a recursive, like you're adding stack frames basically every time you find a new parentheses and you're looking for the matching parentheses. And that's not very fit for zero knowledge proofs. You might have like loops within loops. You might end up trying to do recursion in a situation that doesn't really like recursion in the pure constrained zero knowledge side. And so the alternative is instead we could just keep track of the nesting depth and keep track of the locations of the matching parentheses and do all of our recursion or stack handling in unconstrained, and then do a single linear loop through our input in the constrained side to just check that all those properties are correct. And this doesn't have an easy translation like nesting depth. I don't know how to translate that to a lot of other problems. But there's a common pattern that you add these extra bits of metadata that allow you to tell locally that things are valid more globally, and you do ideally like a linear sweep doing those constant time checks. Another example that often is less thought of as a search, or at least I think of it less as a search, is things like limit order matching or LO game matching. So you have with like limit orders, you basically have like these ranges of things that can match, and you need to do a search through possibly hundreds and hundreds of pairs if you were just brute forcing it. But instead, we can just say, oh, well, the constraints are we need a match within these boundaries, and we need to ensure that it's a valid match. But then once we have that, actually checking that we have a valid match could be very fast. Similarly, but I think it's a slightly simpler case for matching ELO scores for difficulty for like matchmaking chess or some other multiplayer game. You probably want to do some extra checks to make sure that like the same two people aren't playing that over and over again, right? Which kind of ruins the math for ELO scores. But other than that, you can basically just check that people have ELO in the database and it's correct and it's within the range for the game mode that you're looking at. So searches, I mentioned, are just one component, but there's another approach that is very broadly applicable to unconstrained functions, and that's whenever we have something invertible. And we can kind of massage the function a little bit to make it a little bit more invertible. But let me explain the premise, which is if you have a function that's invertible, you don't actually have to calculate the function itself. You could instead calculate the inverse, and then you simply ensure that the function and inverse are match. So multiplication is cheaper than division. Nth powers are much easier than nth roots for integers or like over a field. Field logarithms and like elliptic curve logarithms can be very very computationally intensive to calculate, but they're very cheap to validate. So you don't ever need to calculate one of these in a zero knowledge proof. If you have unconstrained functions, you can simply validate that it's correct and calculate it out of band with more specialized algorithms. Um, it's possible to extend injective functions into invertible functions by retaining lost info. This is a little bit abstract, but the idea is that when we have an injective function, we have, or even like less than injective functions. The idea is that when we have a function and we look at the amount of data that's preserved by the function, we can kind of think of it as an invertible part and a non-invertible part where we're losing information that can't be recovered. So for example, like the absolute value function just removes whether or not the input is positive or negative. The idea is that if we retain that piece that's lost, we retain, well, the output is, let's say, of -3 is 3 and a negative sign separately. Then we can go back to -3, and all of a sudden, the absolute value function, in some sense, is extended to an invertible absolute value function. The codomain or the output of the function is no longer just integers. You have the extra negative sign Boolean to keep track of, but now it's an invertible operation. Absolute value is not super interesting, but a more, I guess, common example is sorting. Sorting is not often considered to be an invertible operation because, like, if we have 3, 2, 1, we sort it to 1, 2, 3. How do we get back? Well, if we retain the original input and we look at the two lists as a permutation between the two lists, then all of a sudden we have that extra piece of data that tells us how to get back to the original order. There's a couple other ways to represent or encode that original order, but it doesn't particularly matter. Any of them will allow us to validate that we had the original data. A more specific example is if we have 10 mod 3, it's kind of one component of the div and mod. So if we include 10 div 3, then all of a sudden we have an invertible function, converting from pairs of numbers to pairs of numbers, assuming we don't divide by 0 and such, right? And then, like, speaking of not dividing by 0, if we have like a much more specialized domain, like if we have only square numbers, then the square root is invertible. If n is divisible by m, then division is invertible. But we do have to check that our premise holds in a more constrained, on the constrained side. And then for another kind of broad pattern, in general, we can kind of split this up into two different steps. We can validate that the output is within our expected constraints, and then we can validate that it came from the input. So for sorting, we're saying that we need to make sure that all of the output elements are exactly the input elements, and we need to make sure that the output is sorted. So we can do that by checking a shuffle or checking that there's a valid permutation between the input and output order of the list. But alternatively, we can also check it more specific, check them individually, if that makes sense. So this one is, it's hard to come up with examples of this because it's kind of just an abstract split into the two halves. But a more complex case, I would say, is like if we have an execution trace for like a virtual machine, we can kind of think of that as, well, we're checking that the end of the execution matches what we expect. So like perhaps the end of a virtual machine says that there's a transaction constructed by some user to another user. So we can validate that separately from just saying that every step of the execution trace is valid. And this can kind of like help factor the problem into more modular pieces. More broadly, we can kind of compose any functions in Noir. So that includes unconstrained functions and functions that call unconstrained functions. So if we sort by x divided by 3, and as I mentioned, the sorting uses unconstrained functions for shuffles and such, we get 3 kind of layers of unconstrained calls. The division by 3, the raw sorting itself of just making sure that we have the output, and then checking the shuffle. And these will be three separate, I mean, they might be optimized together, but generally these will be three separate kind of foreign calls out to the unconstrained environment. And the idea is that we can kind of like build up the amount of information that we know about the intermediate values in our transformation, and we can use that to not have to duplicate some checks. So if we've already sorted the list, it becomes cheap to prove non-existence of elements, doing the unconstrained search for the gap between where we would expect it to be in the sorted list. And there's other cases like this, but generally if you know properties like sorted largest values, all of these are valid, all of these have been checked with certain things, often you can reuse those. And you want to make sure that when you do another unconstrained call that you're not having to recheck too many of those details. And if possible, you can do those final checks later down the pipeline where they wouldn't have to be repeated. And I'll talk a little bit more about this, but you do want to be a little bit careful with the overhead from doing unconstrained calls with very large inputs or outputs, mainly large arrays. Because implicitly, when you return from an unconstrained call, and let's say you return like 100 U8s, which I'll use in an example, we're checking that all those U8s, like none of the values are larger than the maximum U8 value. So like if you're doing a couple unconstrained calls, you probably won't notice the difference, but if you're like iterating, as I'll show, that could become a larger overhead. So we can kind of think of the constrained and unconstrained as like a partition of the call graph. So here I have the black nodes are the constrained final checks, and then the red nodes are the unconstrained. The idea is that if we find a large group of unconstrained calls that are all contiguous, each one calling the next, we may be able to fuse those together and combine assumptions to reduce our overhead. So let's give an example. I mentioned the array of U8s. I'm going to compare a function that maps every value in the array to the value plus one, and one that does, and then I'm going to apply that 100 times. And then the second version, we're just going to add 100 to every value in the array. It's easier to mention now, but because this function only has one input and this other function has two inputs, the second one takes one more opcode, but they're virtually the same function. We're mostly going to be comparing how we can call them differently and constrain them differently. So I have three examples, and I'm going to just kind of skim over them real quick to illustrate the point. But in all three, we have our 100 U8s as our input. We create a mutable variable to store the output. In this case, first we simply increment the array, every value in the array 100 times, and then assert that every value in the array is equal to 100. This is the most expensive approach, and while it will ensure that every value is equal to 100, it takes over 10,000 ACIR gates. Now, if we simply do our checks in the middle, in between every increment, and we make sure that each value is that value plus one, the compiler is able to figure out the intermediate values or the intermediate constraints for these unconstrained calls, which before it had to kind of group them all into one very unknown unconstrained call. Now it can be a bunch of less unknown unconstrained calls because we check in between each unconstrained call. And with this, it actually reduces the amount of gates by over 2/3. With the additional information of these assertions, we're able to get the number of ACIR gates down to 300, and the unconstrained opcodes is the same at 225. Finally, if we simply do it in one pass, we save 100 gates by reducing the number of range checks that we need, and we're able to get it down to just 200 gates. So definitely do experiment with adding constraints that are in between unconstrained calls to help the compiler tell more information in between those kind of black box calls to it. But if you can fuse a large number of array calls, it will likely be one of the fastest approaches, at least until we figure out how to automate more of this in the compiler. And then what about, so you've figured out an approach. Maybe you've found a subset of your program that is a search or NP related or something like that. And now the performance isn't quite, either you don't know if it could be as good as it could be, or you already know that you want it to be better, right? So how can you debug performance? Well, couple of things that really help with unconstrained functions is looking for unnecessary duplications of arrays that could be passed back and forth between unconstrained and constrained. Avoid duplicating assertions between the unconstrained and the constrained versions. So for example, we don't need to check that the output is sorted or double check that the output is sorted on the unconstrained version. We're already checking it on the constrained side. Use the flame graph tool to look for key areas where unconstrained code could be used. This would either be large blocks, or as I'll mention in a moment, it could also be kind of leafy areas at the tips of the flame graph. And we have this Noir profiler tool to help with it. So just a quick example of of the flame graph looks like. It looks like, I think, a lot of other flame graphs. You can either look at the executed opcodes, so the unconstrained side at runtime, or the compiled opcodes. These are also the unconstrained opcodes because Brillig. And there's kind of two ways to try to figure out how to improve performance. You can either start at the base of the tree and say, oh, well, clearly SHA-256 var is taking up all the time. And then the second biggest thing is hash final block. So then you can narrow in and say, okay, well, is there anything in hash final block that I can fix? But then the other thing, which is harder to show in this example, is these little tiny tips sticking out at the very top. Well, I don't know of an easy way to just kind of flip the flame graph upside down. What can happen is that many of these tips are repeated operations, or even operations like add or multiply that are very simple, but could be improved by unconstrained calls. So it's worth looking at the tips of the flame graph as well for any large chunks and seeing if it's repeated and seeing if those could be potentially batched or moved into unconstrained. All right, and then for unnecessary copies, the tooling is still a bit work in progress for this, but there are a couple of methods that you can use currently. Look for unnecessary duplication of arrays. We're improving ownership semantics and just a lot of features around this. So I do expect this to be easier as time goes on. Currently, we have somewhat hidden ownership semantics and copy on write when in unconstrained mode. And this is to try to make the kind of like the borrow checking side of, or the lack of borrow checking to be as easy as possible. But when you're trying to debug performance, all of a sudden our somewhat conservative copy setup can cause some issues potentially. So you can count array copies for your Brillig program runs with this count array copies command. It'll tell you exactly how many array copies for that specific run to help you benchmark it a bit. Arrays have reference counts, which are incremented per reference to a variable containing an array. And we're only copying the array if the reference count is bigger than 1. So there are many cases where we can prevent the need for a copy, but it just kind of like with NP, there are some very challenging cases where for us to ensure that everything is safe, we might do an unnecessary copy. And for a larger program where performance is more critical, it can be worth looking at this more manually and more intentionally. And like for the most amount of detail that I think makes sense for this, you can print what we call the monomorphized AST of the code. It's an internal representation of the program that includes explicit clones, which increment reference counts, but do not necessarily cause a copy. Because if the reference count only ever reaches 1, we won't make a copy, even if it says clone, which is a slight difference from what people might expect. So in conclusion, there are many ways to improve performance with unconstrained functions. We can do searches, we can take advantage of the inverses of a function, or even kind of extend functions into invertible ones. We can look at more abstract approaches like validating our input and connecting the input and output. And overall, this is somewhat similar to using a coprocessor, where you can expect some overhead from moving to and from the coprocessor, and you can also expect that some operations might be a bit faster or slower than you're used to in other languages. Look for cases where the amount of compute is much greater than the amount of data, or at least noticeably larger, because those are the cases where unconstrained functions can really shine. If the proportion of data is too large relative to how much compute, you might not actually gain a lot of benefit from using the unconstrained functions. It counterintuitively might be much faster to do everything constrained, or a lot more of that constrained. And then definitely remember that all essential crypto needs to be constrained. What do I mean by essential crypto? Well, any final checks and any checks that are part of the crypto algorithms that you incorporate need to be constrained. So for a Merkle tree is one of the easiest examples. Looking up the path in the Merkle tree does not need to be constrained because it doesn't guarantee whether or not somebody is in the tree. But that final checking all of the hashes that match the root, that does need to be constrained, because otherwise there's not really guarantees that it'll be done correctly. And with that, thank you very much. And any questions?
Anyone? I have some. If no one has any questions, I'm happy to kind of take a step back and ask. I have like a whole list, so I'll start with one. So since there maybe are some beginners who are listening, maybe on 2x speed as I like to do for my recordings, I'm wondering if you could share a little bit for those new to ZK in simple terms what is useful about unconstrained functions and why it's such a powerful concept for improving performance in ZK circuits.
Yeah, definitely. So ZK circuits translate, we're trying to translate general CPU instructions to the closest we can get to elliptic curve crypto, so that we can use this cool property that one person does the work and knows the data, and the other person can check the work without running the whole computation themselves, or knowing the exact data that's being checked. And the issue is there's a lot of overhead between the normal CPUs and elliptic curves. So, and some problems simply can't be translated straightforwardly. So unconstrained functions do two things. One, they make it possible to run functions that otherwise we couldn't fit into elliptic curves and couldn't easily fit into circuits. And secondly, it allows us to offload often a large amount of the computation. And it looks a lot like offloading things to GPUs. So when you have a GPU, you can't necessarily run everything in the GPU, right? Like we can't run our crypto in the unconstrained side. They're super fast, but there's some overhead from moving things back and forth. We basically, by supporting unconstrained functions, allow you to have like a coprocessor or GPU style additional computation that can run much faster in some circumstances, and generally can make your computation in your circuit a lot smaller and a lot cheaper.
Awesome. And then kind of building off of that, maybe at a high level, you could talk about like some of the trade-offs. So when you use unconstrained functions, how do you decide what parts of a circuit to make unconstrained, especially when the overhead could maybe negate some performance or maybe introduce security issues?
Yeah, definitely. So generally, I would say if you have a large program, there's likely a lot of room for unconstrained functions. But in general, you want to look for areas where you're kind of grinding on the data, so to speak. Any areas where you're doing a lot of compute, and then ideally it's checkable stuff. Like if you're doing like a large amount of compute that is a little bit more like proof of work, then that might not be able to be validated depending on how the proof of work works. But really, you likely want to put as much into unconstrained as possible because of the performance benefits. Now, because of the security, like maybe you're under constrained, maybe you haven't moved all of your constraints properly. This is a bit more of an advanced technique, and yeah, there's more room for error than just doing everything constrained. if you're not entirely sure, I would recommend that you just do things constrained. Um, and potentially, I mean, you don't necessarily need to understand this stuff super deeply to use a library that has already figured out the details.
Makes sense. And maybe you could share also some potential like real world use cases where unconstrained functions might make something that otherwise would be totally impractical feasible. It could be totally just made up. And then especially if you maybe have seen some in production applications yourself, like ZK Passport or other places, those would be great examples, but it could just be totally theoretical too.
Yeah, I really like the example of just kind of like doing an Ethereum proof, like an Ethereum storage proof, because the final check of an Ethereum storage proof is we're basically like checking some signatures, checking a block validity thing real quick, and then we need to check like some Merkle tree paths. And then all of a sudden we know the balance of a user in an application like way deep into Ethereum, right? So that the constraint side is super straightforward, but how are we connecting to the Ethereum network? How are we figuring out where in the storage this application is? You know, how do we know that this user is connected to this application? Like all those other details um, can be really complex and involve technologies that aren't even possible in zero knowledge circuits, right? Like it might require like talking to an Ethereum node or anything like that, right? Um, so that's the idea of like how unconstrained can be generally applied. And as far as production use, I'm not entirely sure about the exact usage for ZK Passport. I imagine that they might have some similar search or Merkle tree lookup type things. It's just like they're super common. But I can say for us, one of the main reasons why Aztec uses unconstrained functions is because we really push the limits of performance for our kernel circuits, for our core layer two circuitry that gets rolled up on, or will be rolled up onto layer one. Um, and I don't have exact stats, but yeah, I don't think our Aztec would really be possible without this.
Hmm. So when you debug and do profiling, so do you have any techniques or tools you recommend for like better profiling Noir programs? Maybe I know like flame graphs can help to like identify like good candidates for unconstrained functions. Maybe if you have any thoughts on like how to find patterns there.
Yeah, so mostly what I already mentioned with just either starting at the bottom of the flame graph or starting at the tips. It gets really domain specific. Like there aren't a lot of really broad approaches. Um, However, I would kind of go through the list of things that I just gave in the talk, which is one, review the list of NP problems and see if anything looks like an NP problem that you're already spending a large amount of time on. I mean, it doesn't matter if you found like 3-sat or graph coloring and it's only 5% of the flame graph, right? So, you know, start with what are your performance constraints? How fast do you need it to be, or like how much do you move the needle by getting it 5% faster? And then you can kind of dig into the flame graph and say, okay, which of my algorithms like are big enough bins to dig in further? And then from there, it's super specific to what you found. Like potentially you found just a search that you were doing by hand with some for loops. Potentially you found an invertible function that you were doing the more expensive side of that invertible function. Uh, but really, like this is fairly advanced, and if you don't find something that's already been done and clearly has a benefit from the flame graph, it could require a bit of creativity.
Hmm. Yeah, maybe shifting gears a bit, then I'm curious, like from your perspective as a compiler engineer, what maybe some of the most interesting challenges were in implementing unconstrained functions, and were there any like surprising like things like hurdles or different design decisions that you guys made?
Yeah, I guess I can say that unconstrained functions look a lot like async functions. And so if I don't know if you've heard of like this, I think it's a blog post, but it's like what color is your function? that async functions often behave so differently than non-async functions that you end up partitioning your entire code base into two copies. And we were able to reduce this in a couple different ways. One is many functions can be automatically translated between unconstrained and constrained by the compiler, and that just works. And we also, assuming that your function might be moved between constrained and unconstrained, we have a standard library function that allows you to check which environment you're in, and use that to change how you run the algorithm for performance. I did see a question in the chat, but
Oh, that was just me. I shared the link to that. I had not seen it, so I was like looking at that really quickly. That's cool. So I wanted to share it. But maybe
cool.
one follow up, I guess, like what are improvements that you're excited about, just maybe in general for Noir, but especially those around unconstrained functions. Now that we're post like version 1.0, are there any features that you think will make it easier to use unconstrained functions, add more safety?
Yeah, so as we approach 1.0, I would say most of the features around unconstrained functions have already landed. Um, I mentioned the stuff around array copies. We are in the middle of trying to pin down some of those semantics and add tooling to make it easier to deal with array copies and debugging their performance. Um, but in general, I think we're trying to improve any kind of tooling around unconstrained functions, and there's some talk about potentially working on a tool that would help know whether you're under constrained, whether you've used the boundaries properly. We do have an existing tool that will tell you if you completely forgot to constrain an unconstrained part of the circuit, but it's not currently very aware of the semantics of the program. So if you have like if-thens, it might mess up the analysis or make it a little bit less use, not mess it up, but make it a little bit less useful or informative. Um, and in general, we're really kind of working on testing and performance at the moment. So there's just a number of cases where unconstrained functions could have bugs that we haven't tested yet, or because we haven't really pushed the performance of some of the like the detailed components that are required for unconstrained functions. Like I mentioned, we have range checks, but in some cases we can actually reduce the number of range checks because they're repeated. Um, the more that we test, the more we can work on optimizations, the faster this will be.
Hmm. And how does Noir, especially Noir's approach to unconstrained functions, compare to what other ZK languages like say Cairo do for like complex computations? So what like advantages does Noir have in this model, especially around like how Noir has implemented unconstrained functions?
Yeah, for sure. So most languages don't support unconstrained functions much at all. Often what you might need to do is add extra parameters to your entire circuit, not just the single function, and accept those inputs that are effectively the results of the unconstrained function. Then on top of that, you'll need to find an implementation in another language that matches, your field element computations, your big lower endian integer mathematics, like all of the specific details that you have in, for example, Cairo. And then you're effectively making this the unconstrained side on top by using what we call at Noir like an oracle function, or a function that calls completely out of the system. Um, so it is possible to use similar techniques in other languages, because at the end of the day, all you're really doing is adding parameters to the whole circuit and running these other programs in a slightly different environment, or not slightly different, but a rather different environment. Um, but as far as I'm aware, only Noir tightly integrates those two environments in a way that you already know that you have a second language that can be run quote unquote async, that is faster than constrained circuits, that all the endianness and field element details match between the two of them. So you can kind of, in some cases, in the ideal case, you can actually forget that you're moving in between constrained and unconstrained functions. They're both Rust functions, and yeah, they have slightly different performance characteristics, but um, by more tightly integrating it allows development to be faster. It allows more easy debugging. Like if you have a bug, do you know which environment if it's in? If you don't have a environment containing the two, um, and really, I mean, another question that we get is like, oh, unconstrained functions. You're literally saying that you have part of the code that's not checked, like it's not constrained. Um, and so we do require like safety comments, explicit annotations for where you're calling an unconstrained function. So you don't, for example, accidentally translate a constrained function to unconstrained with our, like I mentioned, we have the automatic translation or anything like that. You always explicitly know, okay, when have I entered this kind of sidecar asynchronous environment?
So you mentioned Rust similarities. You mentioned like the array stuff in especially unconstrained context. Maybe for developers coming from Rust, what is like some key differences that they should understand about Noir's like memory and ownership model?
Yeah, so as I mentioned before, we have somewhat hidden copy on write semantics. So I would say that there are very few similarities with Rust's ownership model and borrow checker, and it's just different. It's just completely different. Um, Other than that, yeah, I would vaguely compare unconstrained functions to asynchronous ones, but ours are, I would say, a lot easier to use than futures and asynchronous and in Rust, because we can do the automatic translation and we just have a different set of constraints. But how I generally think about using them outside of the API is quite similar. When you have like some tight loop or something, you're not running every line of the tight loop in a new async call, right? You're trying to bundle up that whole batch of computation and you're trying to put it out into async. Like similarly, like if you have like you're just incrementing one like the integers in like 1,000 values, like you don't want to do that like every single call is async. Like you want to try to bundle up as much as possible and be aware of how much data you're translating back and forth across that async boundary. Um, I mean, similarly, like you can't translate necessarily everything across the async boundary, like it has to be send. Um, and we have similar constraints that I believe a recent one was that we only have partial support for passing function pointers across that boundary. You can't pass mutable things across the boundary because we can't keep track of the mutations outside of the environment where where we could keep track of them. So there are a couple similar restrictions. But in some, the exact API looks pretty different, and we hope ours is easier to use. But how you kind of generally think about what parts of the program could be async or could be unconstrained, those are somewhat similar.
Hmm. Yeah, that's helpful. I think just thinking through the mindset of how to approach that is helpful. But yeah, I think those are most of the questions I had. And yeah, this was a great talk, Michael. Thank you for joining us and sharing. The recording for all of you guys that are here live will be posted by end of day today. Also on the YouTube, we have like a YouTube playlist for NoirHack where you can watch all of these. Maybe some of you are watching this already on 2x speed as I will probably be doing later. So thanks again, Michael. Thanks everyone for joining and listening. And we'll also share the slides later today as well. Thanks, guys.
All
See
right,
you in the
thank you so
next
much for having.
workshop.
Thank you. Take care.
Bye, Michael.